Hello everyone. So today we're going to continue on 10.2. So 10.2 just basically talk about some of the applications of differential equations. So we're not talking about any difficult differential equation, how to solve them yet. Just simple application on differential equation in general and some of the basic differential equation that you already learned. So it is next section that we'll talk more about how to solve a differential equation or rather on differential equation that you haven't seen before. So to start 10.2, the first thing I want to talk to you about will be the following. So far you have encountered differential equation already. And there are basically two types of differential equation that you know how to solve. So let's go over the two types. The first one is called direct integration. The first type. So direct integration would be differential in this form. So let's say given a differential in this differential equation in the form of dy over dx equal to f of x. This type of equation, this type of differential equation can be solved by directly integrating the equation. By what we call direct integration. So what does that mean? Well, basically mean the following. If you're given dy over dx equal to f of x, then you can say, well, that would mean that dy equal to f of x dx. And then you can then say, then that would mean that y must equal to integral of f of x dx. And of course, don't forget the plus c. So this type of equation always have a solution. In this form. And you will later learn that a lot of differential equation that we're going to be doing, we're actually not going to try to solve the differential equation the way that I just showed you right here, but rather just simply have an idea based on the type of the differential equation that we have an idea as to what is the solution going to look like. As a matter of fact, some of the recurring things that we're going to be doing in this class while we're solving differential equation, what you think would be a natural things to do, which is to try to solve a differential equation basically using integration, because after all, you learn in basic calculus, integration is the direct inverse of differentiation. But as a matter of fact, what we're going to try to do throughout this year is to try to learn how to solve a differential equation without actually using integration. And you might be wondering why, but the answer is simple. Integration is hard. It's very difficult to do integration. As a matter of fact, there's a lot of functions where we cannot take the integral of it. Unlike differentiation, where you pretty much know everything that you need to know to find the derivatives of some function that I'm going to give you. But integral is very simple. It's very difficult. And there are a lot of integration of very simple function that does not exist. So we're actually going to try to define what kind of differential equation we have and what would the solution go look like, and then try to feed the solution into what the specific equation is. So we'll see more of that later on. Now, but of course, this one is called direct integration, so we can actually integrate to find an answer. So therefore, I'll give you a very simple example to illustrate this concept. Let's say we have dy over dx is equal to 1 plus x squared to the negative 1 power. And in this case, I'm also going to give you initial condition. Let's say y of 1 equal to pi over 4. And the question going to ask you to solve this initial value problem. Remember, if I give you a differential equation and an initial condition, then what we have is the initial value problem. So how would we do this one? So pretty simple, because as I say, it's a direct integration problem. So dy over dx is equal to 1 plus x squared to negative 1, or technically speaking 1 plus x squared. So therefore, this right here is our f of x. So our equation is in the form of dy over dx equal to f of x. So based on what I told you, the solution should always be in the form of, and which in this case would be integral 1 plus x squared dx plus c. And I'm hoping that you remember what function has a derivative that is equal to 1 over 1 plus x squared. And that is the tangent inverse function. And now what I need to do is basically find c. So to do that, I'm going to plug in what I know. So I know that pi over 4 is equal to tangent inverse of 1 plus c. Seem to me the tangent inverse of 1 is just so happen to be pi over 4. So therefore, pi over 4 plus c equal to pi over 4. C must be 0. So therefore, now I know my answer. Y equal tangent inverse of x. So this function not only satisfies the differential equation, but at the same time satisfies the initial condition. And therefore, this is considered to be a particular solution. In this case, subject to the given initial condition. And then what is this right here? This is often referred to as a general solution. All right. So pretty straightforward. So this type of differential equation is probably one of the most straightforward one, provided that you can actually form the integral. But if you can do the integration, then it's probably the easiest type of differential equation. Because it requires no special technique other than the fact that you need to know how to integrate. Pretty easy. Now then move on up to a second type. So this type, the second type is what you learned back in BC Calculus. This type of differential equation can be solved by using a process called separations of variables. So what is separation of variables? So separation of variable will be a different type of differential equation. And a differential equation, in the form of g of y dy over dx equal to f of x is called a separable equation, differential equation. So of course the term separable, meaning that you can separate the variable. And so this equation we can solve this type of differential equation using a technique called separation of variables. So hopefully you remember what separation of variable is from BC Calculus. So once again, what I'm going to show you is what does the solution look like. The solution of a separable differential equation in this form of g of y dy dx equal to f of x is basically this. Integral of g of y dy equal to integral f of x dx. So the idea obviously here is that to separate the y and the x at two different spots, and then after you do that, you would then be able to integrate to come up with the correct answers. So that's the general idea of a separable differential equation. So I'll show you a very basic one. Actually one that we kind of see from 10.1. So 10.1, we look at the graph, a slope field or direction field of a differential equation of this form. dy over dx equal to negative x over y. Now, from last video on 10.1, you notice that the solution set the integral curve form concentric circles. So that's what I'm going to try to show you using separation of variable to solve this differential equation and show you that the relationship between y and x would actually form a circle. So let's see how that works. So the first step will be the following. So we're going to start with dy over dx equal to negative x over y. Notice that it is not in the form right here. G of y dy dx equal to f of x. What I'm going to do is I'm going to move the y over. Now, once I move the y over, now I see that this right here is my g of y. This right here is my f of x. So now, based on what I told you, the solution to this differential equation will be in the form of integral of g of y dy equal to integral f of x dx. So essentially, some of you probably remember learning basic calculus, where you basically kind of multiply or move the dx to the other side and then integrate both sides. That's essentially how we come up to this form. And now I'm going to integrate this. So when I integrate this, I get 1/2 y squared equal to negative 1/2 x squared plus c. Remember, you do have to put a plus c. And normally you put the plus c where the x is instead of where the y is. So that way you don't have to worry about solving for the variable y if you need to and become in issues. And here, what I'm going to do is the following. What I'm going to do is I'm going to multiply the entire equation by 2. If I do that, I would get y squared equal to negative x squared plus some kind of constant c. Notice that this c is not the same as the c on the step before, but it's still just a constant that we don't know. So I'm not going to keep track of what operation we've done to this constant, because eventually it just becomes one constant. And the next thing I'm going to do is move the x squared over, and therefore become this. And in this step, what I'm going to do, I'm going to go and call this c r squared, and now form this equation. That is the equation of a circle. And that's the reason why the integral curve for this differential equations are circles. As a matter of fact, in this case, notice that what we choose r to be will form a different concentric circles of different radii. That's basically how all the family of integral curve are generated, by changing this constant that define what the equation is. Now, here's something interesting to think of. If you think about it, this kind of arbitrary constant c squared is kind of dictating what the solution would be. And in a sense, this becomes like a parameter of sorts. Because when I plug in different value for this, I will now form different circles. And as a matter of fact, that is how we go eventually interpret it. Is that the integration constant becomes some kind of parameter that form our vector space. So we'll talk about that eventually as we go on into more discussion on differential equation. So now the last thing I want to show you is this. So the last thing I want to show you would be to talk about, to show you some example, some kind of application of differential equation. I mean, we studied differential equation. We obviously could study differential period from the enjoyment that we got from solving a difficult differential equation. And that's definitely should be good enough for anybody, right? But if in case it's not, then we also should learn that how can we use differential equation in other disciplines. As a matter of fact, remember, a math system is created so that other people can use it to describe what they're doing. Okay, well, the most important thing is that we are trying to use this mathematical system to describe things that's actually happening around us. So what I want to do is to show you some example that will illustrate some application of it. So the first application that I think I want to illustrate to you would be an illustration in chemistry, a mixture problem in chemistry. Okay. So what I want to do is kind of give you a problem to work on. Okay. So here's a simple problem that we can do. Okay. Ooh, I don't know what happened to this thing. Okay, but okay, I guess it looked kind of weird, but that's what it is. Actually, you know what? Yeah, I think that's it. I'm going to leave it the way it is. I don't want to fix it. It's okay. So suppose that a full tank... So this is a basic mixture problem. A mixture where you try to dissolve some kind of solution into a tank. And how that solution would work when you have some kind of flow rate that changes the solution. So here we describe the following scenario. Suppose that we have a full 100-gallon tank. So when I say the word full, that means this 100-gallon tank has 100 gallons of liquid inside. And this 100-gallon tank contains 150 pounds of salt. And of course, this 150 pounds of salt can be replaced with any other chemical that you want. So it doesn't have to be salt. It could be anything. It could be some kind of acid solution. It could be some kind of chemical. It could be some kind of pollutant. It could be anything. But let's say it contains 150 pounds of salt, for our case, in the solution at the time t equal to 0. Now a solution, a salt solution with a concentration of 2 pounds per gallon is being added at a rate of 2 pounds per minute, 2 gallons per minute. And then after fully mixed, the solution is flowed out of the tank at 2 gallons per minute. Now, notice the important part here is that the tank has a solution that coming in at 2 gallons per minute. But also at the same time, a solution must flow out of the tank at 2 gallons per minute. In that way, it will maintain the concentration, maintain the volume of the tank to be at 100 gallons. So essentially, this is what this scenario basically describes. We have an 100-gallon tank with a pipe that flow in, and then a pipe that flow out. So a solution go in to the tank, and this tank have 100 gallons of liquids inside. And then excess liquids flow out. So how quickly are the liquid going in is 2 gallons per minute. To maintain the volume of the tank to be at 100, the liquid also exceed out at 2 gallons per minute. What we go try to do is to try to find, we go try to find a function s of t that model the amount of salt in the tank. Okay, so how do we actually figure this out? So first of all, you have to understand is that the amount of salt inside the tank is changing because of the salt liquid going in and the salt liquid that's going out. So what we're going to try to do is we're trying to model. So this is how we start the process. See, in order for us to figure out what is a function that can model the amount of salt in the tank, in this case, I must start by understanding how it is changing, and therefore result in forming what we call a differential equation. The concept of how do we describe this is based on something that you learn in BC Calculus, where in BC Calculus you learn that the net change of something is often equal to a rate in versus minus the rate out. So here, the simple concept is that the net rate, that means how quickly the salt is changing inside this tank, is equal to how much salt, how quickly the salt is going in, minus how quickly the salt is going out. So let's try to figure this out. So first of all, if I let S to be a model of the amount of salt in the tank, then the rate of which the salt is changing is defined to be ds over dt. And that equal to the amount of salt going into the tank. So how much salt is going to the tank at what rate? So if you think about it, we do have a concentration of 2 pounds per gallon. So this is our concentration. And then we have a flow rate of 2 gallons per minute. That is the flow rate. Multiply those two together, allow me to cancel out the gallon and give me with a pound, which is the amount of salt, per minute, which is the time variable. So that is the rate of salt going into the tank. Now let's figure out how much salt is leaving the tank. So here becomes the tricky part. What I need to do is to figure out the concentration and then multiply by the flow rate, just like how we figure out the rate in. And the flow rate is simple because that's 2 gallons per minute. So that is fixed, so we know that one. But what is the concentration? So the concentration is actually not fixed because concentration of salt in the tank is dependent on 2 variables. So you probably remember learning that in chemistry. So what is the amount of salt, what is the concentration of salt in the tank? It would be depending on the amount of salt, which at any given time is given by the function S over the volume 100. Notice that one of the reasons why I want to maintain the volume to be constant is so that we don't need to have a variable underneath this number right here. We can just have it be S. So that would be S pound over 100 gallons. So same thing happens. The gallon cancel out, leave you pounds per minute. That become our unit for our rate of change. So therefore, what we have is ds over dt equal to 4 minus s over 550. Because the 2 cancel with the 10, and 2 times 2 is 4. And since the problem told me that there is initially 150 pounds of salt in the solution, therefore we also have an initial condition. So this differential equation with this initial condition describe this scenario of having a 100-gallon tank with 150 pounds of salt, where a 2 pounds per gallon solution going into the tank at 2 gallons per minute with the excess draining out at 2 gallons per minute would show. So notice a lot of these things going on to come with this equation. So now what I'm going to do is simply take this equation and now try to solve it. So how do we solve this equation? So interesting enough, this is a separable differential equation. So we can simply separate the variable and do it. So how do I do that? Simple. The first thing I'm going to do is I'm going to combine these two fractions together first. If I do that, I would have so 200 minus s. And then what I'm going to do is move the 50 over to the other side, and therefore become 50 ds over dt. Oh, I'm sorry. I'm going to leave the 50 over here because I need the 200 minus s to the other side. So I'm going to go and move the 200 over s, 200 minus s to the other side, become 1 over 200 over minus s is equal to 1 over 50 on this side. So now what I have is a g of s and a f of t in this case. So now I have it in a separable differential equation format. So what I'm going to ask you to do is to go ahead and try to figure out the solution. So pause the video and try to figure out the solution. And then when you're done, come back and unpause, and so you can watch, you can see the answers. So I'm going to go ahead and do this. So therefore, that will tell me that it's integral of 1 over 200 minus s ds is equal to integral of 1 over 50 dt. And the integral of this is actually going to be natural log of 200 minus s negative equal to 1 over 50t plus some constant c. If I now move the negative over, that means natural log of 200 minus s equal to negative 1 over 50t plus c. And yes, it doesn't matter if plus or minus because c can be any constant, positive or negative. Get rid of the natural log, meaning that 200 minus s equal to e to the negative 1 over 50t plus c. Now, remember what we talked about in BC calculus. This plus c simply form a coefficient in front of our exponential function. And so now I should be able to, this is absolute value. And now I should be able to figure out what s is. So that would mean 200 minus s equal to plus or minus c. Well, technically speaking, c can be positive or negative. So I'm just going to ignore that plus or minus. And then I can simply just solve for s by saying s would equal to 200 minus some constant c e to negative 1 over 50t. And now if I solve for the initial condition, I would have 150 equal to 200 minus c times e to negative 1 over 50 times 0. So that just go to 1. So therefore c must be 50. And therefore now we have our solution. S equal to 200 minus 50 e to negative 1 over 50t. So that is a function that modeled the amount of salt inside the tank. Now, something I do want you to think about, and we can probably talk about during class, and someone remind me to go over this question during class. Go over the question. So think about the following. So now this equation kind of model the amount of salt in the tank, meaning that if I plug in the t value, this would give me the amount of salt at that moment. So notice if I plug in 0, that would give me 150, which is at the time in the beginning, where the tank contains 150 pounds of salt. And then if I put in, I don't know, 10, that would tell me after 10 minutes how much salt are in the tank, so on and so forth. So here comes the question I want you to think about. Okay, think about this. What if we allow this process, this whole thing, I let this salt liquid continue to come into the tank forever? What would happen to the amount of salt in the tank? All right, so take a minute to think about that. And then, unfortunately, I don't have time to start my second example, so I guess we'll probably go talk about second example in class, or maybe in a second video. So depending on whether I want to do a second video for this, for 10.2. If not, we'll do the second example during class. if I choose to do another video, then we would do it on a second video. Okay. All right. I think that's it for today. So think about the question that I just asked you. What happens if we allow this process, this whole scenario of liquid going to this 100-gallon tank, and we let this process go on forever? What would happen to the amount of salt in the tank? All right. Talk to you later. Bye bye.